Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 1.8 from your textbook. In this section, what we're going to be investigating is sort of a general method for solving some types of first-order differential equations. This sort of general method or general approach is sometimes referenced as change of variables, or more simply, it can sort of be viewed as a method of substitution. What we're going to be doing in this section over the course of this video and the next is looking at some very particular substitutions that apply to some very special differential equations. While we're going to be focusing in this video on what are called homogeneous of degree 0 differential equations, and in the next video we'll be focusing on what are called Bernoulli differential equations, really the sort of point of emphasis for this section is not just on these two special types of differential equations and their corresponding change of variables, but in this technique in general. In other words, that you can take a differential equation that might be more complicated than we're sort of used to working with, but through a particular change of variable or through a clever substitution, you can put it into a format that is much more standard and much easier to work with. So let's get in and take a look at our first sort of special case of this. So to start with, we're going to give a definition. So a first-order differential equation is said to be homogeneous of degree 0. This is sort of a clunky name. A lot of times it's just referenced as homogeneous, but unfortunately, homogeneous is a word that we use several times throughout this course, meaning different things. We'll see that we'll sometimes talk about homogeneous linear differential equations, which mean linear differential equations where that independent function of the function of the independent variable on the right-hand side is equal to 0. We'll talk about homogeneous systems of linear equations, which means that we have a system of linear equations where everything is equal to 0. So sometimes that word homogeneous is used when we're talking about equations that are set equal to 0. So we're going to use the sort of clunkier name here to separate this type of homogeneity. So here we're saying something is homogeneous of degree 0. So putting that little extra phrase degree 0 to make sure we understand what type of homogeneous we're talking about here. So, what does it mean to be homogeneous of degree 0? Well, it means it can be written in this format, where the derivative, so y prime, is equal to a function of y over x. Now, this is a little bit weird, but what this is basically saying is that you can view the differential equation as the derivative of your dependent variable is equal to a function of the quotient y over x. In other words, everything on that right-hand side can be thought about as a function of y divided by x. How do we identify potential homogeneous differential equations of degree 0? Well, we're going to do several examples in just a moment, so we'll basically see how to do this identification. But there's sort of two things you should look for that sort of hint at homogeneous differential equations of degree 0. One is anything that involves a composition of y over x. If you see in a differential equation, a term like sine of y over x, or e to the y over x power, or something along those lines, those are good tip-offs that you might be looking at a homogeneous degree 0 differential equation. Another more subtle way is if you see a bunch of multivariate polynomial terms that all have the same degree. What do we mean by that? Well, remember that the degree of a multivariate polynomial is the sum of all the exponents in that term. So if you see something where you see maybe a term x squared y squared, and then plus y to the fourth, and then plus x cubed y, well, all of those are multivariate polynomials of degree 4, because you have x squared y squared, that's degree 4. You have y to the fourth, that's degree 4. You have x cubed y, that's degree 4. So if you see a bunch of multivariate polynomial terms that all have the same degree, that can also be a tip-off that you're looking at something that is homogeneous of degree 0. And of course, as we do our examples, we'll talk a little bit more about that. Okay, so why are we going to be focusing on these homogeneous degree 0 differential equations? Well, it's because we have this theorem that tells us that if we use a particular change of variable, we can convert homogeneous degree 0 differential equations into something that we're used to. So, this theorem says if you have a first-order differential equation that is homogeneous of degree 0, then the substitution, or if you prefer change of variable, which is the title your book uses, v equals y over x, will convert this into a separable differential equation in terms of v and x. So, what this is basically saying is if you have something that is in this format and you use this substitution, it will become separable, which is a format we are very comfortable with solving. So let's go ahead and prove this and see how this is going to work. So to start off with, we're going to assume that we have a homogeneous degree 0 differential equation. So we're going to assume that we have y prime equals f of y over x. And just to make it a little bit easier, I mean, a lot of times we use the shorthand y prime, but let's just write it out as dy dx to remind ourselves that we're treating y as the dependent variable, x is the independent. Again, this is just a notation change, but this notation here, while this is a little messier, does have the advantage of showing the independent variable. Okay, so now let's go ahead and let v equal y over x. So that's going to handle this side very nicely. Notice that the right-hand side, once we actually plug this in, is going to become capital F of v. But we need to think a little bit about the left-hand side. So let's rewrite this substitution. It's equivalent to saying that y is going to be xv. Right? If v equals y over x, then y is going to be xv. And let's differentiate this on both sides with respect to x. So this tells us that dy dx is the derivative with respect to x of xv. Okay, so now we need to differentiate this right-hand side. So if we do that, well, this would be a product rule. So we take the derivative of x, that's going to just be 1. So we would get v plus, and then we differentiate, we leave the x alone, and we differentiate the v. We're treating v as the new dependent variable here. So we'd get x dv dx. Okay, so we now have that v is equal to y over x, which is the same as saying y equals xv, and we now know we can replace dy dx with v plus x dv dx. So let's go ahead and pop that stuff in there. So we'll put this in on the left-hand side, and we can replace this just manually with v. So we get v plus x dv dx is equal to capital F of v. Okay. Now remember, our claim is that after this substitution, it should be separable. So we should be able to view this as a separable differential equation. Well, notice we have a v and an f of v, so all that stuff is in terms of v. So let's put this over here. So x dv dx is capital F of v minus v. And then, well, notice that this is separated, right? There's the x on this side, there's the f of v minus v on this side. Technically, they're sort of on the wrong side, so we could divide this over, divide that over. 1 over f of v minus v dv dx is going to be equal to 1 over x. Now, of course, when we get into solving and we actually have explicit functions, this moment of dividing this over here is going to be a concern because v is our dependent variable. So if this difference could potentially be 0, then we're going to have to consider those possible extra solutions. But in general, right, since we're just trying to show that it is separable, notice that I've brought this over here. So now we have a function of v with our dv dx equals 1 over x. We'd be able to integrate the left-hand side here as an integral dv, and we'd be able to integrate this side as an integral dx, and there we go. We've shown that this thing is indeed separable, right? Because we've shown that our dependent variable there, independent variable there, that's the definition of a separable differential equation. Okay, so what this basically is, and we're going to do another example of this sort of proof in our next video, is it's basically showing that if you have a differential equation of a particular format, in this case, homogeneous degree 0, and you choose this particular substitution, then it is guaranteed to become converted into a format that we are comfortable solving. So just like when you guys learned about U substitution for integration, this technique does not solve the differential equation for you. U substitution does not solve the integral for you. Instead, it simply changes the format into a format that hopefully it's easier to work with. And in this case, every time you run into one of these homogeneous degree 0 and you use this substitution, you're guaranteed that the resulting differential equation will now be separable. Okay, let's get into a couple examples of actually trying this. So, for our first example, we're going to find all the solutions to this differential equation. xy prime minus y equals x times cotangent of y over x. All right, first of all, I mean, obviously we're in section 1.8 right now, and we just talked about homogeneous degree 0, so that's the technique we're going to assume here. But what would be the sort of tip-off if we just saw this problem randomly out in the wild? Well, It's this right here. The fact that we have that cotangent of y over x, we see that composition, y over x plugged into a function, that's a big tip-off that this thing might potentially be homogeneous of degree 0. To actually show that, though, we need to be able to write it as y prime equals a function of y over x. So let's try to isolate that y prime. So let's begin by just bringing over the y. So x cotangent y over x plus y. And then we can finish isolating by dividing by x. And of course, that's the independent variable, so we don't need to be too concerned about that division. So cotangent y over x plus y over x. Wow, that looks nice because you can sort of see there's a function of y over x, there's a y over x. Yep, this is going to be able to be written as a function of y over x. So now we're going to do our substitution. V equals y over x. And I usually write out all the pieces of it. So I'm going to, every time I do one of these, just to remind us what's going on, I write out this piece. I write out this as an intermediate step. And then I also write out this piece. Now, this one you don't really have to do if you just sort of memorize the steps. But I think it's nice because it shows us how we go from our substitution to what we actually substitute for the derivative. So we're going to have that. We have xv is equal to y. And then I will start shorthanding, though. Y prime is going to be v plus xv prime. And again, getting that is just applying the product rule as a derivative there. So let's plug that in. We'll pop this in over here. So we get v plus xv prime is equal to cotangent. Now this y over x is going to be a v. And then this guy right here, that y over x, is also going to be a v. So we have this differential equation. Now, normally, when we have a new differential equation, we'd have to think, how are we going to solve this one? But because of that theorem we proved, it is guaranteed to be separable. So we know that this should have some method of separating it. We can bring this v over and cancel that out. So we get xv prime is going to be cotangent of v. Then we can bring the cotangent of v over, and we can bring the x this way. So we can get 1 over cotangent of v, v prime, is equal to 1 over x. Now, that is dividing by a function of the dependent variable. So let's just note that off to the side here. Cotangent of v not equal to 0. We'll deal with that at the end. For now, though, this is separated, so we can go ahead and integrate with respect to the respective variables. So 1 over cotangent of v dv equals the integral of 1 over x dx. Of course, here the trick is going to be recognizing that 1 over cotangent is the same as tangent. So there's tangent v dv is the integral 1 over x dx. So then over here, we can integrate this. The integral of tangent is ln absolute value secant v. And then, of course, the integral of 1 over x is going to be ln absolute value x plus some unknown constant. If we want, we can sort of do our standard trick of unpacking by doing e to both sides here. And then, of course, we know that that constant's going to slide down in front. So we can get that absolute value secant v is going to be cx there. If we go ahead and do that simplification, again, remember that's taking e on both sides. Again, actually, we don't even need these absolute values here because, again, choice of constant, we can get away with just getting it there. Then we can go ahead and unpack this by sort of replacing what the v is equivalent to. So we can get secant of y over x is equal to cx. And then finally, I suppose if we really wanted to, although it is a little risky, we could go ahead and sort of apply the arc secant on both sides and get an explicit sort of form for that. Though I would be a little bit cautious about that because introducing like an arc secant function is, well, you know, those inverse trigonometric functions, a lot of times they're restricted inverses like they are for arc secant. So it might be best just to leave it in sort of this implicit format that the secant y over x is equal to cx. So there we go. There's our sort of solution there after unpacking that v into y over x. Now we do need to go back and consider this situation here. So let's go ahead and just pull this over to here. So let's go ahead and consider what happens if cotangent of v does equal 0. Well, we have to figure out what that even means. So cotangent being equal to 0, cotangent is cosine over sine. So for cotangent to be equal to 0, the cosine would need to be 0. So that really means that cosine of v would need to be 0. When is cosine equal to 0? Well, that would mean that v would need to be pi over 2 plus some integer multiple of pi, right? Every pi over 2, cosine is equal to 0, and then if you go another pi radians or 180 degrees, you'll hit another spot where cosine is 0. What does this mean, though? Well, that's y over x is pi over 2 plus pi k, which means that we're actually looking at things where y is pi over 2 plus pi k times x. So those are the things we're actually considering. Now we need to actually check if these things that resemble this, so basically linear functions with these very specific slopes, if those actually solve the differential equation. So let's go ahead and check those. So if we go back to our differential equation, on the left-hand side, it's going to be a little bit messy, but for our left-hand side, well, we would have xy prime, so x. Y prime here would be pi over 2 plus pi k, because the derivative of this is just going to be pi over 2 plus pi k. And then we'd be subtracting y, which would be pi over 2 plus pi k x. And if we look there, that right-hand side, those two things are going to cancel, or that left-hand side, that's going to be 0 there. What about the right-hand side? Well, the right-hand side has that x cotangent y over x. But remember, these things were selected to be moments where the cotangent was 0. So we know that that right-hand side is going to be 0. So these do work. So this is a whole nother host of solutions, right? Anything of this sort of format is also a solution. So we definitely want to make sure we include those in here. We'd be a little bit suspicious about whether or not we could find those solutions in this family. That's probably pretty unlikely. So we might as well include all of it here. We're probably more concerned about missing solutions than we are potentially having some repeats. So we'll say that our solution set, in this case, is secant y over x equals cx. And then also all the sort of linear solutions, y equals pi over 2 plus pi k x. Now, is there a possibility that some of these could be found maybe in this for choices of constants? Potentially. There is always that sort of potential there. If we were being super thorough about making sure that our solution sets never had any sort of repeats, we would want to probably check that. But in this case, that's going to be pretty messy because of the secant function in there. So at least this guarantees we've covered every potential solution. Anything of this format and any linear function with this particular type of slope. So there we go. There's our first example of going through and solving a homogeneous degree 0 differential equation. Really, the sort of big theoretical idea, I don't want you guys to get too sort of lost in the details of the sort of solution set here. The real key idea is that because this differential equation could be written in terms of y over x, the change of variable, v equals y over x, converted it into something that was separable, and then we proceeded our standard way. So the technique we used to solve it is still being a separable differential equation. We just had a sort of preliminary step of doing this change of variable. Okay, let's go ahead and take a look at another one. So we're going to try to find all the solutions to this differential equation, x squared y prime plus x squared equals y squared plus xy. Now, this guy right here might not look as immediately obvious as a homogeneous degree 0 like the previous one did. We don't see it in any immediate function of y over x. But notice that all these things here, all these are polynomial terms, and this is degree 2, this is degree 2, and this is degree 2. So that's a sign that it might potentially be homogeneous of degree 0. To actually try that, we're going to isolate the y prime. So let's go ahead and do that. X squared y prime is y squared plus xy minus x squared. And then we can divide by that x squared. So y prime is y squared over x squared plus y over x minus 1. And notice this term here, if you want, you can recognize that as y over x squared plus y over x minus 1. Notice that's perfect for being homogeneous of degree 0. Everything on this side is a function of y over x. All right, let's go ahead and do our substitution then. V equals y over x, which means that we're doing y equals xv, which means that y prime is going to be v plus xv prime. So again, those are the two components we need. That's just an intermediate step, but might as well write it out. V plus xv prime is going to be v squared plus v minus 1. So there we go. There's plugging this guy into here, and then this v equals y over x makes this side just v squared plus v minus 1. This is guaranteed to be separable now, so let's bring the v over and see how to separate. So xv prime is v squared minus 1. Then we can divide this over here and divide this way. So we get 1 over v squared minus 1 v prime is 1 over x. Again, this is the division that we're going to have to be a little cautious about. So that means v squared minus 1 is not supposed to be equal to 0. We will deal with that in just a little bit. For now, though, we'll go ahead and integrate 1 over v squared minus 1 dv and the integral of 1 over x dx there. Yep. So again, that's our separable theorem, saying that if you can isolate dependent function here, independent function there, you can integrate with respect to each variable. This side, not too bad. That's just going to be ln absolute value x plus c. Actually, in these homogeneous degree 0 ones, this right-hand side is always going to come out at least initially like that, because if you go back to our proof of our theorem, we actually showed that the right-hand side is always just going to simplify to 1 over x. It's the left-hand side that's going to be a little bit more complicated in these. Okay, so on this side, what are we going to have to do with this? Well, we probably need to sort of take this off to the side because this integral here is a little bit messier. This is actually going to be a partial fractions. The reason is here the derivative of the denominator is 2v, so we can't do a u substitution. So we're going to actually have to do this as partial fractions here. So I'll probably go ahead and just do this on a separate page, and then we'll come back. So let's go ahead and integrate 1 over v squared minus 1 dv. So we can think about that as 1 over v minus 1 v plus 1 dv. So we can sort of split that up into its two factors there. Then we can try partial fractions. Well, I say try, but we know partial fractions works. Partial fractions will always help us take care of a rational integral. Since we've got two linear terms there, we can think about this as a constant over v minus 1 plus some constant over v plus 1. We can go ahead and multiply by the least common denominator, so that v minus 1, v plus 1, and get 1 equals a times v plus 1 plus b times v minus 1. Now, if you want, you can actually manually solve this out algebraically, or you can use the sort of fast trick of plugging in v values to make this easier. So if we do like v equals minus 1, well, then this term is going to cancel out. Here, we're going to get we're going to get 1 equals negative 2b, which means that we get b is negative 1/2. And then at v equals, say, 1, well, then this term is going to drop out, and we're going to get 1 equals 2a, because if we plug in 1 into here, and then we get a is 1/2 there. Okay, so we can pop these things in here now, and we can get that we're actually trying to integrate 1/2 over v minus 1 minus 1/2 over v plus 1 dv. All right, at this point, we can go ahead and just directly integrate this. Should be pretty easy. 1/2 ln absolute value v minus 1 minus 1/2 ln absolute value v plus 1. There we go. So there's our integral. We can go ahead and grab this thing and place it back from where we were. Now, let's go ahead and do that. So we can take this over to here. We'll probably give ourselves a little bit more space. So we just figured out that this is equal to 1/2 ln v minus 1 plus 1/2 ln, or minus 1/2, excuse me, minus 1/2 ln v plus 1. And that's going to be equal, like we said, I don't need that equal sign, blah. And that's going to be equal to ln absolute value x plus c. Okay, now, again, that's the major thing in terms of solving the differential equation. We did it. I'm going to do a little bit of algebra now that can be a little bit messy to try to come up with a better format for this. But in terms of solving the differential equation, we should see this, we did it. We did the integrals. We're all done with this sort of technique. But there is a little bit of sort of clever manipulation here that you can do with this. Notice that these 1/2 you can stick back in as exponents here. So we can actually view this as ln absolute value square root v minus 1 minus 1 minus ln absolute value square root v plus 1 equals ln absolute value x plus c. Then we can remember that the subtraction of a pair of logarithms can be thought about as the logarithm of the quotient. So we can think about this as square root v minus 1 over square root v plus 1 equals ln absolute value x plus c. Then we can do our trick of doing e to each side. And of course, this side over here is going to simplify to just cx. And on this side, we can end up with the square root v minus 1 over v plus 1. So that looks tremendously nicer. And then we can replace the v being y over x and get square root y over x minus 1 over y over x plus 1 is equal to cx. And then I suppose we could clear up the sort of complex fraction, multiplying x on top and bottom, and get square root y minus x over y plus x is equal to cx. Now, could we go further? Sure, we could try to square both sides and then maybe multiply this over and then bring this back and get, try to solve explicitly for y. Again, there's no mandate in this class that you must have an explicit form for y. So as long as we sort of simplified it a little bit and gotten it out of sort of at least this messy form with the double ln's and everything, we'll call this good enough. We do have some things that we wanted to check back at the sort of beginning here. So let's go back over here and take a look at these v squared minus 1. So let's go ahead and just check that over here. So what happens if v squared minus 1 is equal to 0? Well, that means v squared would be equal to 1, which would mean we get sort of two potential things we need to check. V equals minus 1, v equals 1. What do those actually mean in terms of our real variables? Well, this would be y over x is minus 1, which is y equals negative x. And this would be y over x equals 1, which would be y equals x. So we've got two potential things we need to quickly check here. Now, just to save us a little bit of time, we'll sort of just check these in our heads just by plugging them in. So let's plug in this y equals minus x in here. So if y equals minus x, let's think about what we're going to get over here. So remember, y equals minus x. Derivative is going to be negative 1. So over here, you're going to get a negative x squared and an x squared. That's going to drop out. On this side, remember we're saying y equals negative x. The square is going to be x squared, and x times negative x is going to be negative x squared. So that side is also going to cancel out. We're going to get 0 equals 0. That one is going to work. If you want, on your own, you can go back and check to make sure that that really does work by doing the left-hand side, right-hand side more formally. For y equals x, well, on this side over here, if y equals x, then y prime is 1. So this is going to be x squared plus an x squared. We're going to get 2x squared on that left-hand side. On the right-hand side, if y equals x, then we're going to get x squared plus x times x. That's x squared plus x squared. That is 2x squared. So we get 2x squared on both sides. 2x squared is always equal to 2x squared. So this one works as well. So we're going to get these two additional solutions. So we should include these on our sort of list. So we can say our solution set is everything of this sort of format, along with things of the form y equals x, y equals negative x. Now, if we wanted to be really fancy, we might be able to sort of notice here that actually the y equals x is actually part of this solution set. If you guys notice, if you choose c equals 0, Then if we square both sides, we'd get y minus x over y plus x equals 0. Multiply this over, we get y minus x equals 0, which means we get y equals x. So actually, this one here is inside the solution set. So if we were being really sort of careful, we would say that the solution set is everything like this, and this y equals negative x. There isn't a good way to get that y equals negative x, though, by choosing any value of c. So really, the cleanest form of the solution set, just to sort of circle that, would be all of this stuff, and this y equals negative x there. Okay, so let's go ahead and take a look at one more example of solving these homogeneous of degree 0, specifically with an IVP. So for this one, we're going to go ahead and we're going to consider this initial value problem, y prime equals sine of y over x plus y over x plus 1, with y of 1 being equal to pi over 4. What we're going to do here is we're going to first prove that this IVP will have a unique solution. Remember, by proving that makes things tremendously easier. By knowing that, it makes it tremendously easier, because then we don't have to worry about, oh, are there other solutions out there? We're just looking for one unique solution. And then we're going to find the unique solution to this IVP. It should be pretty clear that this is going to be homogeneous of degree 0 again, because we have that y over x in there. But let's start with part A by actually proving that it has a unique solution. So how do we prove IVPs have a unique solution? Well, you have two different existence and uniqueness theorems, one that applies to any order linear differential equation. This is definitely not linear because we have a function right there of the dependent variable. So that existence and uniqueness theorem is out. We also have an existence and uniqueness theorem that applies to any first order differential equation. So let's try that one. So we're going to try our existence and uniqueness theorem, first order differential equation. Notice it's already in the format that we want. We want y prime equals a function of x and y. So in this case, our f of xy is all that stuff, sine y over x plus y over x plus 1. Okay, so there's our function in terms of y over x. And then, of course, we also want to study the partial of this function with respect to 1. So we're going to differentiate this, treating x as a constant. Derivative here is going to be a little bit of a chain rule. It's going to be cosine y over x, and then times the derivative of this. Well, the y is just going to become a 1, so we get 1 over x plus 1 over x, and then, of course, the derivative of that one is gone. Are there some discontinuities? Yeah, anytime we're near like x equals 0, there's going to be some issues, but, of course, our IVP is y of 1 equals pi over 4, so that means at near x equals 1, y equals pi over 4, both fxy and df dy are continuous, which implies IVP has that unique solution. So again, remember that there could be issues if we looked at an IVP where, you had y of 0. In fact, y of 0 as an IVP wouldn't make sense because you'd have undefined things there. So there would be concerns if we had an IVP like that, but in our case, the IVP has x being equal to 1, so near that, both of these functions are guaranteed to be continuous, so we know that the IVPs can have a unique solution. So once again, just a quick review of existence and uniqueness theorem for the first order differential equation. All right, now let's go ahead and find the unique solution to this IVP. So we'll go ahead and do that on the next page. So we actually want to try to find this thing, so we're going to use our substitution since it's already in the sort of format that we would like. Let's go ahead and do v equals y over x, which means y is going to be xv, which means y prime is going to be v plus xv prime. So let's plug that in. V plus xv prime is going to be sine of v plus y. There we go. Now this is guaranteed to be separable. We just got to separate it. So xv prime is going to be sine of v, subtract the v over, plus 1. Let's do our division. 1 over sine of v plus 1. V prime is going to be 1 over x. Should we make a note, sine of v plus 1 not equal to 0? Yeah, if we were solving in general, we would need to consider that. But, of course, we know that we're working for this unique solution. And since this unique solution has y equals pi over 4 and x equals 1, that means y over x, which is equal to v, is just pi over 4, which means that this thing is not equal to 0, so we have no concerns there. So we can just proceed as normal. Let's go ahead and integrate both sides. Sine of v plus 1 dv, integral 1 over x dx. Okay, this side, nice and easy, ln absolute value x plus c. This side is a little bit messier, so let's go ahead. We'll just sort of grab this thing here. You know what, the red is sort of a not a nice color to look at all the time, so let's do this in green. We'll take one more page. We'll try to integrate 1 over sine v plus 1 dv. This is a little bit of a trickier integral, but this has a nice sort of trick to it, which is that we can multiply this top and bottom by the conjugate. Notice there's not much else to do because you can't use sub for sine of v plus 1 because, well, you would need a cosine v, so we'll have to use this conjugate trick. So we're going to multiply 1 over sine v plus 1 times sine v minus 1 over sine v minus 1 dv, which gives us sine of v minus 1 over sine squared of v minus 1. That doesn't necessarily look that much better, but keep in mind this is the same as, we can call it that negative, so sine v minus 1 over negative 1 minus sine squared v. And that's sort of nice because 1 minus sine squared v, that's cosine squared. So I'm going to go ahead and apply this negative up here. So we can do 1 minus sine of v over cosine squared v dv. Oh, that's much better because now our denominator is a single term, so we can just apply it to each piece. So 1 divided by cosine squared, we know a better name for that. That's secant squared v. Minus sine of v over cosine squared, well, we can view that as sine over cosine, which is tangent, so tangent v. But then we also have another cosine v in the denominator, so we can think about that as secant v dv. Now that looks really nice. We know that that's tangent v minus, and tangent, the integral of tangent secant is just secant, so there we go. So there's our antiderivative, tangent v minus secant v. All right, let's go ahead and throw that stuff back over. So this side we just figured out should really be tan v minus secant v. All right, no real hope of unpacking this any further because there's not really anything that we can do to sort of combine these together or anything. So let's just pop back in the y over x. So tan y over x minus secant y over x is ln absolute value x plus c. Let's go ahead and solve for our c. So we have y of 1 is supposed to be pi over 4. So that means we get tangent pi over 4 minus secant pi over 4 is equal to ln of 1. Can drop the absolute values because 1 is positive. Tangent pi over 4 we know is 1. Secant pi over 4 is 1 over the square root of 2 divided by 2. So that means it is square root of 2. So we get 1 minus square root of 2 is equal to c. So that tells us our unique solution here is this implicit relationship, tangent y over x minus secant y over x equals ln absolute value x plus 1 minus root 2. And there we go. There's our unique solution to that one. So this one here, again, just another sort of example of solving through and using this substitution for these homogeneous degree 0. Main idea here, though, was that since we had this little bit of extra work at the beginning, we knew that it was going to have a unique solution. So always pay attention if a question tells you that there's a unique solution or asks you to prove that ahead of time, because then when you go into this part here, it's much easier because you know you're only looking for one solution. So moments like dividing by that sine of v plus 1 was not a concern because we knew we weren't anywhere near that. So there we go. We've seen a couple examples now of solving these homogeneous degree zeros using this change of variable. In our next video, we'll look at another class of differential equation called Bernoulli differential equations that have a different change of variable.